Welcome everyone to our first DC Thursday of 2021. Great to have everyone here. I know some of us geeks might be glued to the price of Bitcoin, watching it approach 40,000 USD, but thanks for tearing yourself away from your wallets long enough to join us for DC Thursday. We have a great lineup of shows and interviews for you this year, and I'll be continuing to guide you through that process. Anna and I here have been researching and pulling together lists of folks that we want to join the program, and last year was such a great success. While we're all sort of close to our screens due to the pandemic, that we've learned a bunch and have a great lineup of programs for you for this year as well. So I just want to thank everyone for joining and mention just a couple of announcements before we start. You recall that we do support live questions in the chat, so you can feel free to drop your questions in the chat for our guest, and we'll be happy to try to get to them time permitting. And also, if you want to be notified of the other great DC Thursday shows that we have lined up for this year, you can just hit the subscribe button on YouTube. And also click the bell button, which is the notification button, in case you want to get notified on your mobile device or on your desktop. So today I'm really excited to introduce TD Das. TD is here from Databricks, and TD has been, he has a really interesting history, 10-year veteran of the data world, and hails from UC Berkeley grad school, where he started to work on the Spark project very early with Matei, who's one of the co-founders of Databricks. So TD has been working in the Spark ecosystem for 10 years. He's contributed heavily to Spark as a PMC, as a core contributor. He's also taken the lead on Spark streaming that sort of came down through the ages. So TD, welcome.
Thank you very much for having me here. It's a pleasure to be on this exciting channel.
Yeah, awesome to have you. And I just want to sort of dive in and chat with you about some of your early career experience, because as I mentioned, you have sort of a really amazing past in seeing the birth and the evolution of Spark. And so I wondered if you could share with us a little bit about how you got into this world and what the start of your career looked like.
All right. So yes, as you correctly gave an introduction, that it's been 10 years I've been working in the Spark world. So that 10-year journey started with me joining the AMP lab in UC Berkeley, where Spark, all these projects started. I joined as a grad student. One of my first projects was to help out Matei, who wrote Spark, was writing Spark at that point of time, help out him building that project, testing it out, running benchmarks, typical grad school stuff. And so that's when it started in 2011. It's 2021 right now. Then after the Spark project, Matei and I together started brainstorming further to extend it for not just batch data, but streaming data. So that's where the idea of Spark streaming came into the picture. That roughly happened at the same time when, for those of you who remember, Apache Storm was getting popular as the first open source distributed stream processing system. And we saw that it was very limited in very obvious ways in terms of fault tolerance, etc. So we thought, why not take the Spark engine and push it to in a new direction to make it as fast as possible so that we can run stream processing jobs on it. That led to Spark streaming, a single engine that can do both batch and stream processing. And a consistent set of APIs between batch and streaming, the RDDs and dstreams for those who have played with Spark streaming, the old Spark streaming before. Consistent APIs because they're the similar semantics between them, thus making it makes the user, the developer's life much easier. So that went on for next 3-4 years till around 2014, 2000. And within that time frame, we saw Spark streaming gain a lot of popularity, becoming almost the de facto standard of stream processing. But then we realized, working with hundreds and thousands of developers, we realized the shortcomings of Spark streaming as well. Like, we have to solve the next level of problems. And in the same time, Rust, who started the Spark SQL project, was building the Spark SQL engine. So the natural next step was to kind of take the best of both worlds, take the much more hyper optimized SQL engine and build a streaming engine on top of that to take advantage of the entire SQL optimizer and stuff. And so that led to the next iteration of stream processing engine, the structure streaming engine, since 2015. Um, and that went on, and that now structure streaming has become a pretty much of a standard in stream processing. So that went on till 2018 to 2019. So somewhere around 2018, the same team that built in Databricks that built structure streaming realized after working with, again, developers, customers, etc., that giving nice APIs um, to make it easier to write your stream processing workload solves only half of the data engineer's problems, because ultimately data engineer wants to solve the end-to-end problem of writing end-to-end pipelines that takes raw data and produces data insights. For that, processing only one half of it. The second half of it is storage of data in a structured ways such that it is efficient to retrieve the data when needed, and you get all sorts of uh, data quality guarantees like transaction guarantees, asset properties, etc.
Mm-hmm.
Typically, for last many decades, databases have been the gold standard for it because it gave all those data quality guarantees out of the box. But data lakes on Hadoop ecosystem, etc., didn't have a lot of those properties, and that's where we realized that we need to solve that problem as well in order to make the end-to-end problem of building data pipelines easier, holistically easier. Um, so we started building this newer project, our newest project called Delta Lake since 2018, which is basically a lot more structured but scalable storage
Mm-hmm.
format, similar to Parquet, but imagine all sorts of asset transaction guarantees on top of it, with while maintaining a full history of all the transactions that happened, and being able to travel back in time to query previous versions of the data. So all of those nice things that some of which you expect out of a database, uh, bringing all of that into this data lake world. So Delta Lake is our current most active project right now, built by the
Mm-hmm.
same team that has been working on Spark for last many years.
Got it. Well, that's quite a rundown of projects across the decade.
Mhm.
Let's dive into the streaming stuff a little bit first.
Mhm.
What did you discover was sort of the main use case for the streaming, the early streaming systems that you were working on?
So the main use cases were so the earliest ones had well, the earliest ones, as well as still continues to be the major use case, is essentially ETL. You have lots of data coming in the form of logs or sensor data and stuff, and you want to be able to collect the data and store it for post processing. And you need a system that scales to large volumes of logs, like gigabytes of data coming in per day, per hour. So so on, like if you dial back to the late 2010 late 2000s, where Hadoop MapReduce just came in, that solved the Hadoop ecosystem. The HDFS with MapReduce solved the problem of storing very large volumes of data and processing on very large volumes of data in a scalable manner. What it did not yet solve was doing it in as close to real time in a streaming fashion as possible. That's where that led to the advent of Apache Storm back then, because that was the first system that could
Mm-hmm.
consume large volumes of data from other streaming sources like Kafka, Flume. There were a few others, RabbitMQ, etc., in
Mm.
a scalable manner and storing it on, let's say, HDFS or something, um, uh, in a in real time and in a scalable manner. And so so that the data stored in HDFS can be queried later for ETL. So that was one of the most important use cases right from the beginning, and still continues to be.
And Storm came out of
So
Twitter, right? So that
yes,
was sort
Storm
of
came out of Twitter.
like indicative of the Twitter style data flow, which is obviously, why they
Exactly.
had to come up with Storm in the first place.
Exactly. Yeah, Twitter, they were obviously one of the most real-time products out there, and so they definitely needed the most real-time and
Mm-hmm.
scalable engine at the back. So that's why they came up with this and stuff, which was the start of the whole big data stream processing. But where uh, and we saw the rise of that, but where it Storm did not initially do very well was to provide end-to-end guarantees that if you have uh, one record coming in from, let's say, Kafka, or from whatever source you're reading from, you want that record to be exact present in the final on HDFS exactly once, not duplicated, not missing data. uh, it didn't do very well in providing those guarantees because the way it was architected. First iteration. This is true for any tool which is the first iteration of an attempt to do something really challenging, and that's where that gave us the motivation that we can do better, and we can do it in an engine such that it solves a whole lot more problem, because earlier people used to have two different stacks. One, the MapReduce stack for
Mm-hmm.
batch processing, and the Storm stack was stream processing with different code and causing
Mm-hmm.
inconsistencies between the produced results and stuff. We wanted to solve that problem as well in at one go. So that's
And
what led to Spark streaming.
so
Now,
that was a large design requirement of Spark Streaming, is that it would support the exactly
absolutely,
one semantics. Mm-hmm.
exactly. And going back to your original question, the ETL was one of the large use cases. The other large use case was real-time alerting, which again, Storm providing very low latency, millisecond latency, was very good at. When designing Spark streaming, we kind of realized that a batch processing engine, even if we push it further down, cannot further into like optimize further. It's really hard for it to provide millisecond level latency. So that's another conscious choice we made, that we kind of conjectured that for a vast majority of stream processing engines, be it ETL, be it alerting, and everything in between, second scale latencies was good enough for like 90-95% of the use cases. That's what our conjecture hypothesis was, and we went ahead and built Spark streaming with that limitation, that maybe we'll get to second scale latencies like half a second and stuff, but not lower than that. But that is okay. The other
And,
benefits in terms of usability, in terms of uh, guarantees, etc., that we provide is going to be much more useful for the broadest class of streaming problems
so
than
so
achieving low and
so
achieving millisecond level latency.
and so I guess that's the design decision that led to the micro batch sort of
Yeah,
concept. Is that right?
exactly. And we thought this will be good enough for most of the thing. And looking back, the hypothesis that we made is still true 8-9 years later since we made that hypothesis. So yeah, some decisions were right back then, and because we are still doing micro batch architecture, and it's still, I can claim that 90 high 90s, I couldn't put an exact number, but 90 to 95 or even higher amount percentage of workloads that we see in stream processing is basically second scale latency is good enough.
And do any of the other common frameworks support or sort of are they built on micro batch technology, or is Spark Streaming the main one or the only one?
So at this point, Spark streaming and the subsequent structure streaming are pretty much the only one built on in a micro batch format, because it's one of the only engines out there which really has this exact same engine, like the underlying nuts and bolts,
Mm-hmm.
running both batch
Mm-hmm.
jobs as well as streaming jobs in the exact same job, task, etc.
Mm-hmm.
format, which
Mm-hmm.
makes it easier to deploy and manage as well. That you can, if you have tuned the your setup to work for batch workloads, you don't need any additional tuning to work for streaming workloads.
Mm-hmm.
So
Mm-hmm.
that's only one of the only engines that still does that. So yes, we are the only ones with micro batch, again with the known limitation. But does it really limit everyone, limit anyone, if 99% of your use cases don't care about the limitation?
Got it. Yeah, I definitely understand the argument. Um, and then so then fast forwarding on to structured streaming. So what was the main sort of design goal of an improvement, feature improvement of structured streaming?
Yes. Um, so Spark Streaming, after developing it for 3-4 years and working with developers, we realized the two main flaws of the Spark Streaming's API design. One was that the way Spark Streaming defined micro batches is based on when the data arrives in Spark Streaming. So it basically is to cut off um, data based on the arrival time. So if you're doing sort of windowed aggregations that give me the average of data based on when the data was generated, which is called the event time. Basically, okay, let's take an example. You have data coming in from a sensor and you want to calculate the per hour or per minute average sensor value. So when you say per hour, you care about not when the hour being defined not on the timestamp when the data arrived into the processing engine, but you care about the timestamp when the data was generated in the sensor. So that event time and windows or windowed aggregates based on event time was very hard to do in Spark Streaming because Spark Streaming did not have the first class concept of event time, and
Mm,
incorporating event time in the uh, doing incorporating event time in doing aggregations was very hard in the Spark
mm,
Streaming's DStream API. That was problem one.
mm,
Problem two is that DStream, the API itself, while the operations like the map, reduce, count, those filter, those operations were exactly same as the operations in the Spark's RDD, which is the batch side of things. The classes were still different. So the user would have to do some rewriting of the code to run the same business logic between batch and stream, which is which was a game changer coming from MapReduce and Storm. It's
mm-hmm,
just this a very minor rewrite compared to rewriting
mm-hmm,
MapReduce to Storm,
mm-hmm,
but still not the best. So
mm-hmm,
we wanted to build something that takes the that allows the developer to write one code and then let the engine figure out that based on the intent of the user, run it in one shot on a finite amount of batch data or run it continuously on continuously arriving streaming data. But the code should be exactly the same. No need to
mm-hmm,
rewrite anything. And those are the two main motivations that led to structured streaming.
mm-hmm,
Uh, those were the drawbacks of DStream that led to structured streaming. The other motivations of building structured streaming was to take advantage of the SQL engine underneath. So the SQL engine, the new batch data frame APIs that essentially is a programmatic mirror API of SQL, uh, uh, and which all boils down to the same logical plan. Then the Spark's Catalyst optimizer comes in to optimize it, and Spark SQL engine runs it on with RDD underneath. Taking advantage of all of that all the performance benefits that comes from all that optimization steps and stuff, take advantage of that to do stream processing as well. So that was like a non-D-stream, but a major motivation to build structured streaming on top of the SQL engine. And what we got there for free is you can write SQL, you can use the same data frame API to write your business logic, and then based on a few additional flag outside the business logic, you can ask Spark to either run it on a batch of data or run it continuously in structured streaming with continuously arriving data. So that achieves the best of both worlds.
Got it. So these were all the steps in sort of the evolution of the data processing strategy of the Databricks products, and being able to sort of seamlessly embrace both batch and stream was a key design decision that you made across all of these enhancements. So then I guess the next step, as you mentioned, I think in your earlier comments, was it's not only about being able to process the data in an efficient way that hopefully reuses business logic across even streaming and batch, which you were able to do. But the next stage is then, what about the storage of the data? So did the concept, was the concept of a data warehouse sort of a clear and present thing in Databricks at this time? And how did you sort of sort through that?
Absolutely. Very good question. So basically, for the last 1.5 decades, if you think about how data storage has evolved, the way before, for the last more than half a century, databases and data warehouses built on databases has been the gold standard. Databases gave all the data quality, transactional guarantees, all of those properties out of the box. So it was great at that. But what it was not particularly great at, or it was not cost effective to do, was to scale out and handle very large volumes of data, like gigabytes, terabytes, petabytes of data. It was not built for that. And that is what led to the development of the whole, the original Google MapReduce, and from that Hadoop MapReduce, Hadoop file system, and all of that, as a completely rethinking of the entire architecture, where the scalability is prioritized over data quality. So, and that's what led to the lake house, the data lake architecture,
it's definitely what led to object storage and S3 structures in the cloud first of all, right? Which are very simplistic, but massively horizontally scalable. And so I'm sorry I cut you off, but you were getting to the part about the lakehouse.
So yeah, but before we get to that, it's important to understand the pros and cons of these two alternate realities. One is there were data warehouses on databases which were good at transactional guarantees but not scalability, and data lake was exactly the opposite. It was built for scalability but did not provide transactional guarantees or any kind of data quality checks out of the box. So for the last more than a decade, companies who deal with large volumes of data has had to maintain these two alternate stacks for very high profile data which needs those guarantees, etc. They maintain a data warehouse and databases. For larger volumes of data which is mostly append only and doesn't need that much guarantees, or doesn't need to be that much reprocessing guarantees, they maintain a data lake. Over the last 2-3 years, we are seeing a convergence of this, exactly mimicking in the same way Spark and Spark streaming led to a convergence of the processing stack between batch and streaming being merged together into Spark streaming. We are seeing the similar pattern between these two storage stacks, data lakes and data warehouses. And Delta Lake is one of the tools which is kind of leading the charge of being able to combine that, because Delta Lake is built on the same principles as data lake, as in fully scalable storage, writes, and everything, but takes some of the fundamental core principles of databases, like maintaining a transaction log, and which is atomically updated on every operation, takes that and applies it on the principle. So it kind of combines the best of both worlds
Mm-hmm.
in an attempt to get you the scalability of data lakes
Mm-hmm.
and the transactional guarantees of data bases and data warehouses. And this
Hence
new
the lake
lake
house.
house.
Mm-hmm.
That's the new architecture we have been proposing and driving, with Delta Lake being the vehicle of that. Is the lake house architecture, that you do not need two different stacks. You
Mm-hmm.
can build one stack on top of all the data lake tools like S3 and all of these infrastructure that you are maintaining for data lake, but you can directly leverage all that scalable infrastructure to do all the computation that you have been traditionally doing on data warehouses, move it over to data lake,
Mm-hmm.
thus end-to-end simplifying your data storage architecture as well. And and and, and as I said, that is like the second half of the your ultimate data engineers or data scientists ultimate goal, to derive
Mm-hmm.
insights from the raw data. So
Got it.
over the last decade, we have spent better part of it simplifying the first half, make processing easier, scalable, efficient, whatever. Now we are working to make the second half easier by completely uh, changing how storage should be done,
Yeah,
and building on top of it.
and that makes perfect sense. So what about the actual storage, the file format? Does a lakehouse require a universal file format, or does the data still sort of live in its own disparate file formats depending on the system?
So, so before Delta Lakes, the the common file formats that were used for data lakes were things like Parquet, ORC, JSON, and stuff. And the more structured it is, like Parquet, ORC, the better the performance you get. So it was recommended that you use it. But the common thing across all of this is that these file formats were open file formats, so any processing engine, any tool could read it. And this is
Mm-hmm.
in direct contrast with databases, which essentially maintain their data in a very highly optimized but internal format that only the database's engine can read and nothing else. So, and that was another principal tenet of the data lake architecture, that file formats will be open so that any processing engine can access the data in parallel without relying on a single agent to provide the data.
Mm-hmm. Mm-hmm.
So in Delta Lake, to continue with the same trend, what we do is that we store the data underneath in Parquet file format. So the individual files are formatted by Parquet, but uh, to read the data, you can to read the data correctly, or you need to read the Delta's transaction log first, because the transaction log uh, maintains a log of which are the files that need to be read for you to get a consistent snapshot view of your Delta Lake table. So you
Mm-hmm.
need to read the
Mm-hmm.
log first, which is also
Mm-hmm.
stored in the same file system. Therefore, the log is also scalable, and
Mm-hmm.
the log data is also maintained using Parquet and JSON. So again, the same engine Spark can scalably read the transaction log if the log is large, and allow the system to scale to millions and tens of millions of files. Uh, so you have to read the log first, and then only will you know that which actual Parquet data files to read. So the summary of what it does is that if your system, if your processing engine can understand the Delta Lake format, basically it knows how to read the Delta Lake's transaction log, then you get the best of both worlds. You get the transactional guarantee, snapshot isolation, you get reading consistent snapshots, asset guarantees, while being able to access the data using open formats like Parquet and stuff, and on
And the
scalable scale.
data completely distributed.
Yeah.
So this is a fascinating architecture. And I guess to be able to support all of the asset-like guarantees, some notion of schema, yet at the same time, this horizontal sort of distributed data scale, there must be a lot of tricks involved to doing this. And I guess one of the complaints I've heard about Hudi or Iceberg or these types of systems is that they're quite complicated to run and maintain. Like, what's your answer to that?
So, so I think ultimately our goal with this project is that the developers should not have to think about the complicated problems. We want to make some of the problems uh, like easier and natural. For example, one thing that we majorly do is in terms of schema is we have schema enforcement. The way it works is that, okay, think about if you're using a Parquet table, there is nothing blocking you from accidentally writing a bunch of Parquet files in a Parquet table
Mm-hmm.
directory, which are of a different schema and format than the rest of the data. And then your table is essentially corrupted because you have data in inconsistent formats. So, and the major reason that happens is that the tools that are writing into the table does not have any knowledge of what is the existing data in it, what is the schema of the data present in it, and therefore it cannot check what it's writing is valid or not. Um, that's where Delta comes into the picture, where because it maintains all of that metadata information in the transaction log, before doing any write, it can successfully enforce that is the data being written in the correct schema or not. And then it can take it a step further that, and this is where making things simpler for the developer comes into the picture, is that it can do automatic schema evolution. For example, if you have new data coming in that has an additional column, which is, and that new schema with an additional column is perfectly consistent with the old schema because you're just adding a new column of data, it will identify that and automatically evolve the schema of the table in the metadata that, oh, now the table has a new column and that's okay.
Mm-hmm.
So, and the user doesn't have to like think about it how you would have to do it in the pure SQL world, in the
Mm-hmm.
old school
Mm-hmm.
database way. You'll have to do alter table, add the column, and only then you can write it. Here it can
Mm-hmm.
be a lot more
That's
seamless.
a
You
great
just
feature.
flip a
Mm-hmm.
flag that turn on schema evolution, and then if you have a streaming pipeline that is continuously writing data into a Delta Lake table, you flip that flag for schema evolution, and if your data happens to have new columns added and stuff, it will automatically get added without your manual intervention, thus making the developers, the data engineers life much easier, that it doesn't require manual intervention. But it is
Got it.
safe because, for example, if the data comes in where it is incorrectly changing the data type of a column, it will block that. It will fail when it is supposed to fail because the schema change is not correct. But if it is, it will allow things like new columns added, etc., uh, when when it is safe to do so. And these are some things that we made a very opinionated policies on what schema changes are allowed and what are not, in order to minimize downstream confusion. That is something that we believe Delta has done it better than other systems like Hudi and Iceberg.
Got it. Got it. Great. Well, that's a super compelling vision. And I want to just take a question from one of our audience,
Mhm.
Mayank, who's asking, can you help with understanding the benefits that a lakehouse will bring if we want to power ML AI solutions? So how does a lakehouse sort of apply to the machine learning world?
Absolutely. Great question, Mayank. So I mean, that is ML and AI is one of the biggest motivation for unifying these two
Hmm.
data lake and data warehouse worlds into lakehouse. Because think about it, what used to be what it used to be earlier. So data that was locked in the database data warehouse, ML systems could not read that data because only databases could read that data. So the way that people used to integrate data warehouses and infrastructure is to explicitly export the data from the databases format to an external format like Parquet.json, uh, and only then would it. Uh, Give me a minute. I'm getting a call for. Let me handle the call. Sorry about this. Okay. Thank you. So where was I? So yeah, so people would have to export the data from the database into an external format like Parquet, JSON, CSV, whatever, and only then the ML systems could read it, which is extremely time-consuming, resource-consuming process to export it every time, because the ML systems could not directly read the underlying data in databases. With data lakes and lakehouse, you can have uh, you can have the best of both worlds. You can have a very fast, efficient SQL query engine, just like databases accessing data, but ML systems can also directly access the data without the need to export and stuff. So
Because of the
that is the
open
point
file,
of
because of the
lakehouses.
open file formats.
Exactly,
Mm-hmm.
because and that is the point of lakehouse, that you can have one single infrastructure that drives and allows any processing needs, any analytics needs to be built on top of it, be it
Mm-hmm.
SQL for BI analysts or be it MLAI for data scientists, all in the same way in an efficient manner.
So in practicality, are you seeing that this vision is actually being sort of embraced by the market? Are people where before they probably had a warehouse, and maybe a data lake sort of just by default because people were storing data in S3 and all kinds of different places. They probably had a time series database maybe, or some other kind of OLAP database. Like they had, all these different data structures. Are you seeing all of these converge and people are sort of spinning down systems that used to exist and essentially migrating them to Delta Lake?
The change is, it's still a very nascent concept. I think
Mm-hmm,
as
mm-hmm,
technology, not just Databricks, but we are not there yet to kind of
mm-hmm,
completely move. I think we're building that. It obviously takes years for any technology, any new technology, a new paradigm to mature. I think, but the change is happening. I think this in 2020 we have seen in our customer base a lot of uh, use cases that were traditionally done using dedicated data bases or dedicated key value stores, uh, being transitioned over to something like to Delta Lake, to make it more cost effective and
mm-hmm,
cost effective, scalable, and efficient.
mm-hmm,
So that change is happening, but it is still the early days. But it's
mm-hmm.
good to know that there is this is the trend that we are going to see for the next 2, 3, 4 years. That there is going things are going to be converging more and more.
Mm-hmm. Got it. So what about the immediate product roadmap for Delta Lake? What sorts of major enhancements are you working on now that you can share with our listeners that they should be prepared for in the near future?
So, absolutely good question. I think some of the major work that we are doing in Delta Lake are things like pushing the boundaries of schema evolution. And schema evolution is something that very few systems can effectively do. And but it, as I already explained, how it can make a developer or data engineer's life much easier, with making it more like much less manual intervention needed whenever your data types or data schema changes. So schema evolution is something that is a very hard problem, and nobody has done it effectively in the past. So this is we are basically the cutting edge of that, of doing that. And so we are things that we are working on is pushing the boundaries of that schema evolution. For example, one of the things I'm personally working on right now is Delta's, unlike other systems, directly supports the merge SQL operation, which basically, for those who are not familiar with what the merge SQL operation is, it allows you to upsert data. So if you have data based on a key, if the data is, so imagine you're computing aggregates based on, so which is essentially key value data, right? You want to inject, or for keys for which the values don't already exist, you want to insert those key values, and for keys where the value already exists, you want to update them. So this simultaneous upsert operation for a set of key values can be done using this merge operation. Now,
Got it.
uh, Delta Lake is one of the first this sort of scalable systems that supports the merge SQL operation directly, and schema evolution on top of merge is one of the most cutting edge things we have done, and we're still continuing to work on it. And that is something no one has even come close to. So traditional database, some of the traditional databases do support merge operation, in fact advanced syntax of merge operation, but nobody supports schema evolution on top of merge. Like while you're upserting, you can evolve the schema. So these are the kind of really cutting edge stuff we are working on right now.
Got it.
And we'll continue to push the boundaries for the next few years.
Great. Well, we have another question from Rick. Rick is asking, how is Spark trying to smoothen the reuse of algorithms, i.e. JAX or PyTorch, in a lakehouse environment?
That's a good question, and it's a complicated one. So let me kind of elevate that question into the general problem that data scientists face is that they want to get the best insights or build the best machine learning models from their data. So, and for that, the ML world has realized that there is always that no single tool can provide the best machine learning model in all situations. So for different problems, they need to build different machine learning. They need different machine learning tools to get their best machine learning models. So that means that there is a need for a platform that can accommodate whatever tool that the user wants to use as easily as possible, which means, and now that need translates to how the platform needs to be architected at different levels. So at the Spark level, what we have been doing over the last few years is that we have made some of our ML APIs a lot more non-Spark friendly. For example, we have built these sort of we have modeled our APIs in a closer to how scikit-learn APIs look like, so that users can seamlessly transition their code between scikit-learn and Spark MLlib to make it easier to try out both tools. Then, in a different approach, people who are familiar with pandas, the pandas data frames, we have built pandas data frames in Python. We have built, which has a different set of APIs than Spark's data frame. We have built this new project called Pandas. Project for pandas called Koalas, which unifies the APIs and gives a Panda equivalent API for Spark data frames, so that just changing an import allows you to take your pandas code and run it on Spark. So at the Spark layer, we are making it easier to integrate and move back and forth seamlessly between Spark and other non-Spark tools to make developers' life easier, so that they can use whatever tools it is that best suits their needs. There isn't one tool that satisfies everything. That's one level of what we are doing to make things more developer friendly. At a higher level, if you think in terms of the entire analytics platform that Databricks provides, we are making Databricks also a lot more non-Spark friendly by incorporating all these other tools already in our platform, so that you can have, so that users don't need to manage their images or their developer environment, etc., to bring in PyTorch, bring in TensorFlow, bring all of that explicitly. Our platform provides that out of the box,
Right.
already installed and stuff. So the moment you start, you can use our notebooks or our platform to run Spark MLlib jobs as easily as TensorFlow jobs,
Got it.
because the platform provides both. So
So
this is a
these
good
these
problem. We're tackling at different levels.
so these enhancements aren't specifically due to the lakehouse structure, the lakehouse architecture. It's just sort of a general Databricks product strategy decision that you want to enable developers to run other machine learning algorithms sort of easily and have them easily plug into Spark execution.
Yes, yes. Well, I wouldn't say it is not entirely tied to the lakehouse stuff,
Hmm.
because uh, while we are, so I think these are parallel attempts. While we're making it easier to have one platform to run both kind of jobs, TensorFlow as well as Spark MLlib, we also need to be able to enable these other tools to directly read the Delta Lake format, so that these other tools can directly, independent of Spark, read the same data that is present in the lakehouse in Delta
Mm-hmm.
Lake. So we're definitely uh, working on making our the Delta Lake format more openly accessible and more integratable into other tools, uh, by providing APIs to, so that other tools can write connectors to directly read the Delta Lake format independent of Spark. So that is also something we are working on in parallel. So it's not exactly very intimately tied, but they are not
Got it.
independent either. So, but ultimately we want the data to be democratized so that anybody can read it from any tool, and
Got it.
have a single platform where you can use any tool to read that data.
Got it. Well, I wanted to switch gears a little bit, TD, because
Mhm.
you have such great experience, obviously, with so many different types of architectures and trade-offs and tools and systems. Um, in terms of folks out there who are looking for career advice, I'm curious. You and I have spoken previously about sort of the difference between the data engineer who consumes the tools that you're building and then
Mhm.
your type of work, which is maybe a little bit more tied to distributed systems. Can you give any folks out there who are looking to sort of deepen their appreciation of distributed systems and other fundamentals that they need to be able to think architecturally in the way that you're thinking? Like what would you encourage them with, and how would you encourage them to sort of study up and get started in deepening their knowledge in these areas?
That's a very good question. So, yes, so I am more like a system engineer who build the tools, who has been building the tools that the data engineers actually use in practice. So they are the actual heroes of their organizations who are
Mm-hmm.
using the tools to actually solve the actual problems. Now, the current state of affairs is that there are so many, until the world has converged in these different ways. Right now there are so many different tools out there that it is often very hard to understand or what is the right tool to use for solving your problems. And that is
Mm,
the real problem, one of the real problems that the data engineers face on a day-to-day basis. Like, how do they design and architect their data processing pipeline using what is the right set of tools to solve their problems. And given this variety of tools, it's I think it's become more crucial than before to understand these each of these tools with a little bit more in depth, the architecture of these tools behind
mm-hmm.
the scenes, behind the APIs, to really reason about what is the right tool for your purpose. And so I think it is absolutely important, more so now than 5-10 years ago, to for data engineers and data practitioners who are writing or designing these pipelines to spend a bit of extra time and effort to understand these tools a little bit more, to understand what the system architecture behind these tools, understand what each of these tools are not good, what they are good for and what they are not good for, in order
Mm-hmm.
to make more educated decision when they're designing their stuff. Um, and I think that is something that can differentiate a good data engineer from a great data engineer.
Mm-hmm.
So it is not to trivialize the problem, but it is easier to build a solution using whatever tools in a quick and dirty manner that works once and scales out to future downstream uses, that works one time for your current needs. But
Mm-hmm.
it's a whole different challenge to design it to make it future proof for
Mm-hmm.
future downstream use cases that needs to work using the same pipeline. And making those kind of architectural decisions that are future proof requires that in-depth understanding. So
Mm-hmm.
I highly recommend data engineers and data practitioners to who are building pipelines to spend the time and effort to understand these tools a bit better.
Mm-hmm. And I dug out a talk that you gave, TD, that I think might sort of help further folks' deeper understanding of some of these
Mm.
concepts on designing ETL pipelines with structured streaming in Delta Lake. So we'll drop that in the chat, but I think that
Mm.
that's a good example of a talk that will help people go a little bit deeper and really start to ask, sort of more prescient questions specifically regarding what they're trying to accomplish and start to consider the architectural trade-offs of different choices.
Mm. Yep.
Do you have any other advice for folks who are early in their career? I guess specifically someone in the audience, Santosh, he's asked, how do I become a data analyst, but I'm a mechanical engineer? What do you think about people sort of transferring into data from other engineering disciplines? Like, have you seen any tried and true sort of path or type of education or mentorship that works?
So absolutely, I personally have a number of friends who have done that transition from other non-CS
Mm-hmm.
uh, uh, background to data analytics, data science backgrounds. I think it's very important to. I think the right way to do it is starting from uh, finding the right materials to dip your toes in data analytics. I think there's a lot of material out there. There are MOOCs in Coursera, edX, and stuff. Databricks, we also provide a training those tutorials which are those specific to the Spark and Delta Lake and that kind of platform. But there are also tutorials that are geared towards data, uh, the beginner data analytics. There are MOOCs built on top of Databricks platform for doing that as well. So there's a lot of material out there that that starts from absolutely the scratch on how to start becoming a data analytics person.
Mm-hmm.
Uh, it's so I think the challenge is to put in the time and effort and the patience to start on that new path. I think
Mm-hmm.
I've seen people who have uh, been impatient and not been successful in doing so, but people who have been patient to power through uh, the initial hurdle and become very successful data science data analysts.
Yep.
So, uh, so power through. I think that's one
Mm-hmm.
of the things I would like to really encourage. That it is incredibly rewarding at the end. And people do make that jump successfully, but you have to have the patience because the start will be slow, and that's okay. It will. It is worth time putting the time and effort.
That's right. That's well said. Well, we're almost out of time, TD, but I just wanted to ask you one parting question, and that's
Mhm.
in regards to the data ecosystem at large. We saw such amazing things happen in 2020. There's many startups that are popping up and getting increased amounts of funding, and so many companies in the space are doing well.
Mhm.
Not just Databricks, but Confluent and others. I'm
Mhm.
just curious. Besides this whole sort of Delta Lake and Lakehouse effect, what are the other trends that you're excited about for 2021 and the data ecosystem at large?
That's a good question. Let me think. I think there. I think convergence is a common theme.
Hmm.
I, convergence in terms of tools and architectures. Like, for
Hmm.
example, Kubernetes, for example, is a one big trend I've seen. Like
Hmm.
earlier, there were 100 different ways of managing your microservices on raw bare metal VMs and stuff.
Hmm.
Um, Now Kubernetes is becoming like a singular way of managing these, and all the clouds support some form of managed Kubernetes service, so which is a, a proof that how the right architectural decision or the right tools designed with the right goals in mind can lead to convergence of
Hmm.
different fragmented tools. And
Hmm.
so uh, these are the kind, so convergence is, I think, that over the last decade we have seen an explosion of tools, not just in data but in terms of infrastructure and stuff. I think the next decade is going to be more about convergence of these tools and infrastructures.
Yeah, I couldn't agree more. There's so much fragmentation in the data world, and I spent some time last year writing a few articles about that. There's so many different tools, and I think that you're absolutely right that there obviously has to be some convergence, and I think it's important also, as you mentioned, to really understand and be able to weigh the underlying architectures and trade-offs so that we start to merge these things in a meaningful way that's actually future-proof, and that doesn't just solve the volume of data that we have now, but solves the volume of data that we anticipate in 5 or 10 years, which will only explode through IoT and healthcare data and all the other types of data that are sort of coming online with these systems that we're building now. So
Yep.
tech is just the first frontier. And now I believe that this whole big data movement is spreading to the rest of the world as well. And so we really haven't seen anything yet in terms of scale.
Yep.
Well, thanks, TD.
Cool.
It was great to have you here.
Thank you very much for having me here. This was a very wonderful conversation.
Appreciate it. So just a couple of comments as we wrap this up. Please leave us comments in the feedback form that's in the chat that we've posted. It helps us know what you like, know what you don't like, and know what we can do better. And finally, if you're an engineer who's interested in starting a company, I personally am having office hours every month with engineers in our community who want advice in getting their startups off the ground. So please reach out to me directly and let me know if you're interested in participating in one of the office hour sessions. Those are designed for the community to support other engineers who want to start companies in 2021. So remember to hit subscribe, and we will look forward to seeing you for our next DC Thursday. Thanks.
Thank you, everyone, and bye bye, and stay safe out there.